In today's video, we shall take a closer look at the concept of impulse. So, what is impulse? Impulse is a physical quantity that is involved in describing the mechanics of an object that is involved in a very short duration collision. What do we mean by that? Let's assume you have a wall and you have a ball that is approaching that rigid wall, and at some point in time it will come into contact and collide with it. Then it will rebound in an opposite direction. So the collision between the ball and that rigid wall takes place there for a very small amount of time, in the range of, let's say, milliseconds. You can also assume this duration as the contact time between these two objects. If we assume the mass of the ball is m, the initial velocity is vi, the final velocity is vf, there is obvious change in momentum associated with that ball. It is the final momentum minus the initial momentum of that ball, which in turn simply becomes m times vf minus vi. The change of momentum of that ball is what we call the impulse in this collision. As you can see, impulse is a vector, and it has the same unit as that of momentum, kg meter per second. Now let's take a closer look at what happens there during the contact. What happens there during that very short amount of time that accompanies the change in momentum is some kind of force is being exerted on the ball by the wall. And that we know to be the case because force is quite simply the change in momentum over the time interval. Since we have the change in momentum associated with the ball and the contact time is delta t, there must be a force associated with that collision. This expression is just another form of Newton's second law of motion. So what causes the momentum of the ball to change is that force that is being exerted by the wall, that rigid wall, on that ball. If this force, or that force, is causing the momentum to change, and we know the change in momentum is the impulse, then we can relate this force to the impulse. And it simply becomes force equals impulse over the short time interval. It's important to realize that the time interval must be very short whenever we are discussing the concept of impulse. This expression right here that enables you to make the transition from this to there is known as the momentum impulse theorem, because it connects impulse to the change in momentum. And this force right there that's causing the impulse is known as the impulse force. And the unit is, of course, newtons. As simple as that. Now let's look at this expression. So now we can write impulse as F delta t. The application of this equation is follows. Suppose that you can model a collision by a force-time graph. Since the collision is a very small duration collision, it could be something like this. So this spike occurs in a very short amount of time, delta t, measured in the units of milliseconds. And as you can see, in that time interval, the force acting on the object, in this case, let's say on the ball, due to that rigid wall, increases from 0 to a maximum value during contact and then drops back to 0. So that is a maximum force. The area under this graph is what we call the magnitude of the impulse, because that is exactly what this equation is describing. So if you are given a force time graph and you're asked to compute the impulse, all you have to do is to determine the area under that FT graph. Simple as that. Let's look at this problem. A force that is variable in magnitude acts in the negative direction of an x-axis is applied to a 0.5 kg ball for 25 milliseconds. The ball is initially moving at 14 meters per second in the positive direction of the x-axis. The impulse is a magnitude of 33 newton-seconds. Now find the ball's velocity after the force is applied. So initially the ball is going in that direction with a velocity of 14 meters per second, I hat. We know the force that is causing that impulse is acting in a negative direction of the x-axis, so it's going like that. What that means, the impulse is also going in that direction, namely in minus I hat direction. So now it's time for us to use the impulse momentum theorem, which says impulse equals the change in momentum in order to determine the answer for part A. We know the magnitude of the impulse is 33 newton-seconds and it's in the direction of minus I hat. The change in momentum is the mass of the ball times the final velocity, which we don't know, minus the initial velocity, which is 14 I hat. And you can solve for the final velocity of the ball. Turns out to be minus 52 meter per second I hat. So the magnitude is 52 meter per second and the direction of the velocity is along the negative x-axis. So that is the answer for part A. Now let's do part B. It says find the average magnitude of the force in the direction of the impulse. Now we know the direction of the impulse is minus I hat because that is also the direction of that force. The average magnitude of the force is related to the impulse as follows. It's the impulse over the time interval. Remember, we are calculating the impulse force here. So we know the magnitude of the impulse, which is 33 newtons seconds, that one right there. The time interval is 25 milliseconds, so 25 times 10 to the power minus 3, and the answer should come out in the units of newtons. And the answer is 1,320 newtons, and that solves the problem. The second problem, associated with FT graph. Graph below shows the approximate plot of force versus time during the collision of the 60-gram ball with a wall. The initial velocity of the ball is 30 meters per second perpendicular to the wall. The ball rebounds with approximately the same speed, also perpendicular to the wall. Find that maximum force. As you can see in the graph, F naught is the maximum force during the collision. So let's assume that is the wall, and you have this ball hitting that rigid wall like that initially. So obviously the velocity is minus 30 I hat meter per second, and then it rebounds with the same speed in an opposite direction, so 30 I hat is the final velocity. So minus 30 is the initial velocity. So we can apply the momentum impulse theorem here, so where impulse equals a change in momentum. However, how do we calculate this impulse? Now we know impulse is just the area under that force time graph. So all we have to do is to determine that area. There are 3 segments to this area. The first one is half times 2, so that is that length, milliseconds, so times 10 to the power minus 3. And this height here is F naught. Now this one has the same magnitude, half times 2 times 10 to the power minus 3, because that interval is again 2 milliseconds, times F naught, that height right there. And finally the rectangle in the middle, the length of it is 2 times 10 to the power minus 3 milliseconds, the height is again F naught. So the total area is this plus that plus that. So over here, it will give you F naught times 10 to the power minus 3. That one will give you another F naught times 10 to the power minus 3. And this one is 2 times F naught times 10 to the power minus 3. So 4 times 10 to the power minus 3 F naught is the impulse in terms of F naught, the maximum force. So let's keep in mind we are just working with the magnitude at this stage. So next, let's determine the change of momentum and the magnitude of it. So from this diagram, the change in momentum is the mass, which is 60 over 1,000 kg, times the final velocity minus the initial velocity. So that means it is 0.060. The final velocity is 30 I hat minus the initial velocity, which is minus 30 I hat, which will give you 3.6 kg meter per second I hat. So the magnitude and the change in momentum is quite simply 3.6 kg meter per second. And now you see you can determine the maximum force F naught. It is 3.6 divided by 4 times 10 to the power minus 3. And the answer should come out in the units of newtons. And the answer is 900 newtons. And that solves the problem. As always, thank you for watching.